An enolate is what is formed when you react a carbonyl compound such as an aldehyde or a ketone or a carboxylic acid derivative with a strong base. Returning to the structure of a carbonyl compound, you have a carbon double bound to an oxygen and single bound to two groups. In the case of an aldehyde, one of those two groups is a hydrogen and the other is an R group. In the case of a ketone, they are both R groups. In either an aldehyde or a ketone, the hydrogen that sits on the carbon bound to the carbonyl carbon is called the alpha hydrogen, and its respective carbon is called the alpha carbon. The alpha in this case does not correspond to the carbonyl carbon because that is sort of the ground zero functional group carbon. So we start naming the alpha, beta, gamma from the carbon adjacent to that carbonyl carbon. When that carbonyl carbon is deprotonated, that is, the hydrogen is removed, and the negative charge falls down to the carbon, you form what is called an enolate. An enolate is a resonance-stabilized anion with, in one form, a negative charge on a carbon, and in the other form, a negative charge on the oxygen. In Chapter 19, which is enolates, enamines, and the Michael edition, you are going to see a nucleophilic reaction coming from the carbon of the alpha carbon of this carbonyl. So, quick question at the beginning of this chapter is why is it that it is the carbon with a negative charge and not the oxygen with a negative charge in this enolate anion that forms new bonds to electrophiles? The reason that is that when you attack something with an oxygen, you form something that is not as stable as when you attack it with a carbon. And what do I mean specifically? When you attack an electrophile with your enolate carbon, you form a carbonyl compound, which is very stable. When you attack something with your oxygen, you do not form a carbonyl. So whatever you form there is not going to be as thermodynamically stable. Another reason you can think of here why the enolate carbon reacts is that the carbon, whenever it has a negative charge, even in resonance, is going to be the highly reactive one. So the first 2 minutes there are just a quick note on what enolates are and why it is that the carbon is the reactive species, or the reactive atom, rather, in the enolate anion. Now, the first reaction we learned with enolates is the self-reaction between an enolate and an enolate of acetone and itself. So the enolate of acetone is a compound where the alpha hydrogen has been deprotonated, and so you have a negative carbon bound to your carbonyl carbon, double bound to your oxygen. Now, when the enolate forms, you have that resonance structure, where one of them is a double bond between the carbonyl carbon and the alpha carbon, and the oxygen is negative, and one of them is oxygen double bound to the carbonyl carbon, where the enolate carbon is negative. Now, when you do this on an aldehyde or a ketone, so you could use like acetaldehyde for the aldehyde or acetone for the ketone, it can do this thing called the aldol reaction. This is the aldol reaction, where the enolate attacks another carbonyl. And in this case, where I am just talking about acetaldehyde, I'll do the acetaldehyde example. You attack the same species that you formed the enolate from. So one acetaldehyde enolate attacks another acetaldehyde. This forms a 4-carbon long molecule with an aldehyde at one end and a alkoxide in the middle. So you have an aldehyde at one end and then an alkoxide 1 carbon away from that. And that is called an aldol once it is protonated to form an alcohol, once the alkoxide is protonated to form an alcohol. So now what we have is a secondary alcohol and a aldehyde. And if you add a little bit of heat to this reaction, so that's our aldol product. That is the product of the aldol reaction. If you add a little bit of heat to this product, you can get something called condensation, where a base in solution, because you used a base to form your enolate, attacks the alpha hydrogen of the new aldehyde you formed, and the bonds from that attack go between the alpha and the beta carbon, kicking out your OH group as a leaving group. Now, that is a condensation reaction because it forms water in the leaving of the OH and the deprotonation, so the removal of H. And yeah, so that's what condensation is. Yeah, it's just water leaving. And it happens with heat. So a good way to remember that is that if you heat it up, water leaves. All right. So why does that happen? Why does that happen? It can seem confusing when you first see an aldol product and then so quickly see it taken away and forming this double bond thing. Well, if you check out the product of a condensation reaction, you see alpha-beta desaturation with a carbonyl. And that, to my eyes, is 3 sp2 hybridized carbons in series, which is a conjugated system. Now we know, due to the spreading out of electron density over 3 sp2 hybridized atoms, sp2 hybridized carbons, oxygens, you're going to have stability because electron density likes to spread out. So whenever you have an aldol, if you add heat, you're going to get condensation. One situation where that might not be the case is if you somehow form an aldol that can't be removed. So you form the alkoxide, and then somehow there's no way to deprotonate that alpha hydrogen on the carbonyl, and you can't go forward from the aldol reaction. And there might be some examples where that is the case. So it is good to be wary that sometimes your only product is an aldol. All right. So, and also, if you don't have any heat, your only product is an aldol. All right, so let's continue with the, so I want to describe a little bit the aldol reaction mechanism. So I described the basic one without really explaining why. Well, the reason we want to do the basic pathway for an aldol reaction is that you form the enolate anion, which is a much stronger nucleophile than the nucleophile you'll use if you use the acidic pathway. But if you want to, you can still use the acidic pathway for the aldol reaction. And this involves simply reacting a carbonyl compound with a strong acid in water. So we did learn at one point this thing called ketoenol tautomerization, where an acid or base can cause a ketone to form this thing called an enol, which is a double bond between a carbon and another carbon, and one of those carbons is bound to an alcohol. So, for example, phenol is a good example of a compound that has an ene, alkene, and then the ol. So double bound to carbons, and then one of the carbons is bound to an alcohol. Now, why do I mention enols? Because when you react something like acetone with strong acid, you get a little bit of enol, just a little bit of enol. But the thing with an enol is that that double bond between those two carbons can then attack a carbonyl. And that carbonyl can, for example, be another acetone in solution that has been protonated to become strongly electrophilic. So that acetone protonated can be attacked by the enol version of your ketone. And then you would get, eventually, an aldol product there. Because, well, actually immediately after the attack, you get an aldol product. So you add in to the carbonyl from the enol, and then you have your alcohol, because there are protons already, there's a proton already on that oxygen, so it immediately becomes an alcohol, no protonation step necessary. And then if you add a little bit of heat, you get a dehydration. So we're well set up for dehydration in the case of the acidic mechanism for the aldol reaction. But you gotta add a little heat. All right. So one interesting thing you can do with the aldol reaction, I mean, so far I've described aldol reactions with itself, with your own molecule. I would call that like a self-aldol. But what if you want to do an aldol reaction where your carbonyl being attacked and the carbonyl doing the attacking are different? Well, one great way to do this is just to take the carbonyl that you want to do the attacking and react it with this thing called LDA, which is a very sterically hindered base, and that sterically hindered base is just going to form pure enolate out of your carbonyl. So you would want to take that carbonyl, react it just with LDA in its own flask in step 1, and then in step 2 add in whichever carbonyl you want to attack. And that would be a really clear way, and you need to add excess in LDA, by the way, excess base, because you want all of that carbonyl to be turned into enolate. But that would be a really great way to make sure that you know which one is doing the attacking and which one is getting attacked. But if we want to be super duper sure and we don't want to have to use LDA, what we can do is have the carbonyl being attacked actually be unable to form an enolate itself. So what do I mean by that? We'll say we have acetone, all right? Acetone on one side, and we want that to one side, and we want that to be the enolate. Well, what if we take this acetaldehyde thing, except you got a benzene ring right on the aldehyde? Well, if you have a benzene ring on your aldehyde, there's no alpha proton that can be deprotonated, because that benzene ring is really stable, and there is literally no alpha proton. I mean, you have the aldehylic proton, but that is never deprotonated. You just should never show that. So the aldehylic proton not deprotonated, and so there are no alpha protons there. So you know that's going to be your attacked, your electrophile, and not your attacker, your nucleophile. So in that case, you can make what you can call a crossed aldol. So a crossed aldol is when your enolate and your carbonyl are different compounds. And then you get a product in which you don't just have, one type of molecule that's been added in twice. You have two different molecules added together. All right. Well, what if we want to do this intramolecularly, where you have one carbonyl forming an enolate and the other carbonyl being attacked? You can do that, and it is called the intramolecular aldol reaction. Now, it's still a self-reaction because you have just one molecule, you have one species reacting with itself. However, you need to be very specific here, because the alpha proton that gets deprotonated on your diketone, for example, is going to have to be the one that allows an acceptable ring to form. Acceptable rings are rings that are sizes of 5 carbons or 6 carbons. Really, it's just those two, 5 or 6. And unacceptable rings are like 7 carbons or 8 carbons. I'm actually not sure about 7 carbons. So you really don't want 8. So yeah, you're going to have the enolating carbon anion, enolating proton, be the one that allows a good sized ring to form. So whenever you look at an intramolecular aldol reaction, you're going to want to make sure that the number of carbons that are going to form the ring is an acceptable number of carbons. Alright, so now we're going to draw a very, very fine line between our topics of aldol reaction and enolates and the certain reagents we're going to use with them. And that fine line is going to be from ketones and esters, ketones and aldehydes to esters. I got ahead of myself there. But we're going to be now talking about esters, and we're also going to throw acid anhydrides in the mix there. But first, let's do esters. So here we're moving in a different direction with our reactivity, because now we have only one deprotonatable alpha proton, and that is the alpha proton of the carbonyl on the ester, not the one that's bound to the ester oxygen. That one is not going to be deprotonated because the conjugate base would not be stable. Now, it turns out that when we do an aldol reaction on esters, it is called this thing called a Claisen condensation, and there is going to be a real use to this mechanism, because we can form a beta carbonyl on your beta carbon. But let's go through the mechanism first, and then see how we get that beta carbonyl of an ester. So it's the ester plus an ester aldol reaction, and you get a beta carbonyled ester. So and it's going to be very synthetically useful, and we'll explain why. So what we do is we take your ester. So let's say it was the ester where we have 2 carbons and then an ethyl group. So 2 carbons, and one of them is our carbonyl carbon, and then an ester oxygen, and then an ethyl group. Well, if we react that with itself under basic conditions, we can have one of the esters become an enol, and then it attacks the carbonyl of another ester, and then we get this sort of diester intermediate, and then when the lone pair on one of our on the attacked ester carbonyl oxygen falls down to form a new carbonyl, we kick out the ester oxygen as an alkoxide. Now, that alkoxide is going to need to be handled by an acid workup, because it is going to form an alkoxide in solution, and that could deprotonate your product, which is essentially an acid anhydride, and that is very acidic. So you're going to need to do an acid workup here with the Claisen condensation or the aldol reaction on esters. But anyway, So now we have an ester with a beta carbonyl. Well, with a beta ketone. So what you can do now, well, we have a beta ketone, and we have something that looks a lot like a carboxylic acid. We're going to do hydrolysis. Or we're going to do hydrolysis, but then we're going to do decarboxylation. And the reason this is important is because you can form ketones from esters. So you can go from ester to ketone by this method. And it was emphasized in class, so it is important to mention here. Now, you want to do two things in order to make this happen. One, you want to do H3O plus and H2O to form your carboxylic acid of your ester. This is hydrolysis, which was covered in chapter 18, carboxylic acid derivatives. Then, what you want to do is decarboxylation, because now you have a carboxylic acid with a beta ketone. So decarboxylation allows you to then remove the carboxylic acid entirely and end up with just your ketone. So you started with an ester or a diester, right, where they're both in the same molecule, and that would form a ring, and then you ended with a ketone. And you can do this all in the same pot. So you don't need to sort of go through rounds of oxidation and reduction in order to do this. You can do this actually pretty elegantly. One very important thing that I need to mention when it comes to the aldol reaction of esters is the selection of the base. The base needs to match the ester that you're reacting. So what do I mean by this? Well, if you're reacting an ester where the alkyl chain coming off of the ester oxygen is 2 carbons long, so it's an ethyl group, you need to use ethoxide, because that anionic oxygen species with a carboxylic acid derivative can add right in through nucleophilic acyl substitution and result in transesterification. Well, here, if transesterification does occur as a sort of side reaction, it's okay, because we just result with the same ester that we started with. So, when it comes to the aldol reactions on esters, we're going to do the basic pathway, right, because that is the Claisen condensation, but we're going to make sure that we use the proper base, which is the ethyl alcohol, or the ethyl alkoxide rather, with this example. We cannot use NaOH here. NaOH would cause the hydrolysis of the ester, which is called saponification and ends up with a carboxylic acid. So that would form just a carboxylic acid, and it would be basically the water analog of transesterification. Alright, so we've covered the Claisen condensation. Now, one thing I want to mention about intramolecular Claisen condensation. So remember, we drawn a fine bright line by talking about aldols from carbonyls to esters. But when we talk about intramolecular Claisen condensation, we are going to use the name Dykman condensation. So that is just the same thing I described. You start with esters and you make a beta ketone, and then you could go a step further with hydrolysis and then decarboxylation to form just a ketone itself. But that is going to be called the Dykman condensation. Okay, so continuing on with enolates there, we talked about this thing that is called alkylation. So, one important thing to note about enolates is that you don't necessarily need to react them with carbonyl compounds at all. You can simply functionalize whatever carbonyl you start with to form your enol by adding an alkyl chain to it. So, what do I mean by this? Well, say we start with a beta keto ester. So you have your ester, and then on the beta carbon you have a ketone. Well, if you react that with the correct base to form the enolate, right? Remember, with esters, we need to be very careful about which base we choose. If you correctly choose your base and react that with your enolate, with your beta keto ester, you can form an enolate. That enolate doesn't need to attack a carbonyl. It doesn't need to attack the same species you started with. If you add an excess of an alkyl bromide or an alkyl iodide, you can form an alkylated product. So, what is the advantage of forming an alkylated beta keto ester? Well, we talked before with the Claisen condensation and the Dykman condensation that when you have a beta keto ester, you're only one hydrolysis and one decarboxylation away from a beta keto carboxylic acid, which is then removed into CO2, and you get a ketone. Well, what about if we want to do an aldol or a Claisen-esque thing, except what we want to add is not another carbonyl, but it's the alkyl group? Well, we can start by having already done the aldol reaction, right? Already having formed your beta keto ester, and then we can add the alkyl group, and then we can hydrolyze and then decarboxylate. So the example we did in class was phenylbromide. We had bromine with a phenyl group. Well, if you take phenylbromide and you add it to your beta keto ester, and then you do hydrolysis, which is through NaOH, right? Because this is going to be saponification, and then do your acid workup with HCl, you get a carboxylic acid with a beta ketone. Carboxylic acid with beta ketone, I'm immediately thinking decarboxylation. Add a little bit of heat, carbon dioxide evolves, and what you get is your ketone, right? The beta ketone stays, the carboxylic F's off as carbon dioxide in the air, and then you have your, well, in our example in class, you get your phenyl group on the alpha carbon. Well, what is the use of this? What we've just done is we've added an alkyl chain 2 carbons away from a ketone, which we couldn't do before in one sort of pot. We would have had to do a lot of freaky stuff with like elimination and different oxidation steps. With the ethyl acetic acetate plus base and alkylation, then hydrolyzation, and then decarboxylation, we can actually just do it all in one sort of elegant mechanism. Now, what's important to note is that you don't have to stop with one alkyl group here. So Klein actually gives plenty of examples where you can add 2 alkyl groups. And that would simply be done by adding more base to your product of the first alkylation step. So when you want to alkylate, all you do is draw an arrow from your ester, do the base ester match, do your base ester match on the top, and on the bottom, put your alkyl bromide. And then just do that again for a second step. So for a second step, just draw the same thing with the base match on the top and then alkyl bromide on the bottom, and then you get a dialkylated product. So you don't need to stop with one alkylation. If you have another alpha carbon to deprotonate, you can do it twice. Now, what if our starting material is not a beta keto ester, but what if it's a diester? This is going to be a situation called malonic ester synthesis. So, malonic ester synthesis. We talked about malonic acid when we talked about carboxylic acid derivatives, and that was a dicarboxylic acid. Well, malonic ester is exactly what it sounds like if you think about malonic acid. It is the ester version of that. So rather than protons attached to our hydroxyl groups, we have alkyl groups. And with malonic ester, what we can do after hydrolysis and after decarboxylation is end up with a carboxylic acid with a functionalized alpha hydrogen. Now, this is important because when we wanted to use carboxylic acids in reactions, we really needed to worry about that acidity of the proton. We can't just make an enolate out of a carboxylic acid. It doesn't really work because carboxylic acids are so acidic. What you can do is use malonic ester, which is just a diester, and enolate that, alkylate it, and then decarboxylate one of the 2 carboxylic acids. Remembering back to the cyclic intermediate of the decarboxylation reaction, it actually warrants the production of only one carboxylic acid, or only one CO2. And so in this case, one of the carboxylic acids leaves the CO2. The other one is still around. The other one stays. And that carboxylic acid now has whatever you alkylated your malonic ester with. So the first step is going to be alkylation. The second step is going to be hydrolysis. The third step is going to be decarboxylation. And the product is going to be an alpha functionalized carboxylic acid. All right, so we've covered the real big first topic, which is aldol condensation. Now, alpha halogenation of your carboxylic acid is going to be done through the malonic ester synthesis pathway that I just described. There is another way to do that, actually, when it comes to just straight up a carboxylic acid, which is kind of interesting, and it is called the Hell-Volhard-Zielinski reaction, And what this is a reaction directly from the carboxylic acid right to a functionalized carboxylic acid. But there's a catch. There's only one group that we can add to the alpha carbon of that carboxylic acid. That is a bromine. A bromine. So we learned about this reagent called PBr3, and that can do two things. It can turn an alcohol into a halogenated alkane, and it can turn a carboxylic acid into the halogen acid version, basically like the bromine version of an acid chloride. Well, another thing that it can do is go from carboxylic acid to acid bromide to acid bromide enol, which is always going to be in tautomerization with the acid halide, and that enol with Br2 can react to add a Br to the alpha carbon. Now, all we have to do from here, now that there's a Br on the alpha carbon, is use H2O to do hydrolysis on the acid bromide part. So when you add H2O to an acid bromide where the alpha carbon has a bromine, you remove the carbonyl carbon's bromine and throw in an OH to form your carboxylic acid. Remember, the product of every hydrolysis is a carboxylic acid. So that is what we are going to form in this case. So wrapping up here with chapter 19, we're going to talk about the Stork-enamine synthesis, and then second, the Michael addition. Okay, so what are we talking when we're talking Stork-enamine synthesis? Well, say we wanted an enolate, but we didn't want it to be very reactive. It turns out that enolates are pretty strong nucleophiles, and that's because you have, in one of your resonance forms, straight up an anionic carbon. So that's not going to be a very stable situation when we're talking about the enolate form of, for example, an aldehyde or a ketone. However, when we form the enolate version of an secondary amine, such as pyrrolidine, which is a nitrogen bound to 4 carbons in a ring with a hydrogen, so it's a secondary N with a hydrogen in a ring of 4 carbons with a nitrogen, 5-membered ring, pyrrolidine, and we react that with a carbonyl, we can form this thing that is a soft version of an enolate. Well, what might be the utility of a soft version of an enolate? It is exactly that, not being very strong, not being very reactive. And it turns out that there is this certain kind of addition called the Michael addition that we are going to want to use these enamines with. Well, how do you form the enamine? Let's take our carbonyl and take our pyrrolidine. The pyrrolidine is going to attack the carbonyl and add in, just like we saw when we were talking about addition to carbonyl compounds with nitrogen. So the secondary amine is going to add in, the proton is going to be removed, and then you're going to have, and then there's going to be an elimination on the alpha carbon of your substrate, and you're going to have nitrogen with your ring on top. It's like a little hat with a lone pair, and then single bound to a carbon that is double bound to another carbon. Now, that double bond, it has a similar reactivity to an alkene, but a little bit more because there's a resonance form with that nitrogen with a lone pair. That can react, well, for example, it could react an alkyl bromide to alkylate it. But what's very important is that after it reacts something like an alkyl bromide to do alkylation, what you have is your iminium ion. Well, an iminium ion is very easy to convert back to a carbonyl by simply using strong acid. Strong acid will add your water nucleophile right back into the carbonyl carbon on the iminium ion. And then you're going to get a ketone where you added your enamine. So, why don't we just recap this? You take your carbonyl, you take your substrate, which here was an alkyl bromide, and you decide where you want to attack. You make the enolate of your carbonyl, you attack, and then you turn it back into the carbonyl. So you attack with the enamine, but you're only using that as a carrier to deliver a carbonyl to a certain place. And that certain place is going to be the 1 spot on, or the 4 spot rather, on an alpha-beta unsaturated ketone. So alpha-beta unsaturated ketones are the species that we produced as a result of our aldol condensation reaction. We produced a ketone where the alpha carbon and the beta carbon were double bound to each other. It turns out that this is called a Michael acceptor, because since that ketone is going to have resonance with that double bond, the beta carbon is going to be positively charged in one of the resonance structures. And that beta carbon can then actually be attacked, because the product of that attack is going to be, well, first an enol, but then it's going to be a ketone, which is highly thermodynamically stable. So it turns out that the thermodynamic product is of the addition to an alpha beta unsaturated ketone is going to be where the beta carbon has been added to by the nucleophile. Okay? That's the thermodynamic product. The kinetic product is going to be the one where you attack the carbonyl directly, regardless of the alpha beta desaturation, but the product of that is going to be an alcohol, which is not thermodynamically stable as a carbonyl, as our ketone. Now, you need to be aware of what molecules are Michael donors and what molecules are not Michael donors. So Michael donors that are going to be often used are, well, one are enamine, which is what we use to deliver carbonyl to the Michael position, but others are the enolate version of an acid anhydride, the enolate version of NO2, so the carbon just adjacent to the end on an NO2 group can be a Michael donor. It could be the malonic ester guy with the enolate version of that. It could be the malonic ester guy enolate version where there's only an ethyl group with an ester on one side. There's many options for Michael donor. All you really want to be sure of, which I see as common to all of the options that were mentioned by the Klein textbook, is that they have resonance. They have resonance. So they're going to be stabilizing that negative charge, stabilizing the thing with which you attack your Michael acceptor. Now, when it comes time to do the Michael reaction and form that ketone that is so stable, you can do that with your enamine. You can do that also with enolate. But we're going to want to use really the enamine for that most of the time. When we do Michael addition, we're going to want to use enolate. Okay. So there's one final reaction that we need to cover when it comes to Michael addition, and this is simply Michael addition when it comes to using an enolate of something like acetone. So you got your Michael, which is an alpha beta unsaturated ketone. You have your enolatable carbonyl, which is your acetone, and you have NaOH. Well, the first thing that's going to happen is going to be the acetone is going to be deprotonated, and you're going to have your enolate. Well, that enolate can add in to your Michael. But when that happens, what you get is a diketone, basically. Right, it adds into your Michael, you get a diketone, but now you have two carbonyl groups, and you still have base lying around. So this is exactly what we saw with the aldol reaction, where it's intramolecular with just carbonyls, not talking about esters yet, but just carbonyls. One of them is now going to be deprotonated, the one that forms the stable ring, and then it's going to attack the other, and you're just going to have an aldol reaction. So if you have a 2-carbonyl molecule, and you have extra base lying around, do not stop there. And the person telling you not to stop there is Robinson, who is the namesake of this reaction. So it is the Robinson annulation, where you add a carbonyl as your Michael donor, and then you have a diketone. One of the ketones attacks the other, you get a ring, and then you get, if you add heat, condensation. This is a great way to make cyclic ketones with alpha-beta unsaturation, because remember, when you do condensation, you remove the OH of the aldol product, and you remove the alpha hydrogen. So that forms alpha-beta desaturation. And that was the final topic discussed in class when it comes to the chapter on enolates, enamines, and the Michael reaction.